Alright, now we'll do our second problem for the Bernoulli's equation topic. Okay, in this problem, a horizontal pipe is equipped with a piezometer and a pitot tube to measure the static and stagnation pressures of the flow. For the indicated water column heights, determine the velocity at the center of the pipe. Okay, so we have this piezometer attached this side, and that's our point A, and we have our pitot tube, and this is our point, right, point B. Okay, and we have this height, column height, so, and then in the piezometer we have this 10 mm height, rise of fluid, and then here we have 18 plus 10, right? 18 plus 10 or plus 15 if we are referencing from the center line. Okay, so the problem says we are to determine the velocity at the center of the pipe. Okay, so now let's try to applying now the Bernoulli's equation. Okay, so P1 or PA by rho g plus z sub A plus the velocity at A, PA squared over 2g is equal to P sub B all over the unit weight plus the elevation head plus the velocity head all over 2g. Okay. And now in terms of the elevation, since we are along the horizontal, then that means that the ZA, that the elevation at A is 0, and also the elevation at B is also 0. Now, recall that for stagnation pressure, so we have an stagnation point right here, and what it means that the fluid that's moving is brought into rest or stagnant, then our velocity at point B would be 0. Okay, so this is 0. And therefore, our velocity at A squared all over 2g is just simply P sub B by unit weight minus P sub A all over this one. Now, this is in terms of head, and these pressures, they're actually a pressure difference. That's a delta P, which is just equal to this delta P, right? Therefore, if we substitute all the values, what we get is 2 times 9.81 meters per second squared times the 18 mm. Since it's in millimeters, then we have to convert the 2 meter to be consistent. So now let's solve. 2 times 9.81 times 0.018, and we take the square root, and that's 0.59 meters per second. All right, now let's do another problem. For our third problem, we have a tube is used as a siphon to discharge an oil of Sg is equal to 0.8 from a large open vessel into a drain at an atmospheric pressure as shown in the figure. Okay, so this is our situation. So we have a large open vessels, and we have a siphon. Okay, so a siphon, it's actually a passage of this oil, and there will be a flow rate inside this, because it actually operates in the working or the working principle behind this is the pressure difference. Okay, so it is used to drain, because this one has higher pressure than this one. I mean, from this point, from the entry point, I guess. Now to this point, then there's going to be a flow of the fluid. Okay, so it says here that it is used to drain. Now calculate the following. Calculate the velocity of oil through the siphon. So what is in this A, what is the velocity along this, right, up to point D? And we'll just assume a uniform. We'll just assume or neglect the frictional effects, and we'll just assume for now that this is a constant diameter tube. Okay, so in other words, the tube does not vary in its cross section. Because if it varies, then there's going to be changes in the velocity. But if the tube has a constant diameter, then the velocity throughout the length will just be constant. In our next topic, we will discuss this. We will discuss the flow rate and the effect of the area, if it enlarge or it narrows down, then what's going to be the effect in the velocity. Okay, so for now it's just constant diameter. Okay, for letter B, it says here that find the pressures at A, B, and C. This is our A. That's not inside the siphon, and B is inside the siphon but at the same level, and C, this is the C, and our D is just right here. But we are asked only to find the velocity and then the pressure at A, B, C. Okay, so to start with, let's solve. All right, let's solve for the velocity. Solve for the velocity in the siphon. Okay, so in finding or in choosing the points, this will be our reference point, the point O, because we have values of the pressure right here, right? So this is a good candidate. Plus, we'll also have a velocity, which is just 0 right here. And then, since we have the same velocity at point B, C, and D, then therefore, I guess the best choice is to choose the letter D. Why? Because this one is exposed to the atmosphere, and therefore the pressure right here would be 0. So, considering point O and D. Okay, now let's apply our Bernoulli's equation. So PO plus the elevation head plus the velocity head is equal to the pressure head at point D plus the elevation head at point D plus the velocity head at point D over 2G. So at point O, we have the pressure term is 0. The velocity is also 0. Right? And for this point D, can have this as 0. And now let's consider an arbitrary reference line, and therefore we'll just use ZD minus Z sub O, or the difference in the elevation. So V sub D squared all over 2G is equal to ZD minus Z sub O. Therefore, V sub D is just 2G delta Z. Okay, so 2 times 9.81 meters per second squared times the difference in height. Now, what is the difference? So it's just 4 plus 1.5, so that's 5.5 meters. And if we take the square root, so that's 2 times 9.81 times 5.5. And the square root, that's 10.39 meters per second. Okay, so now since we have the velocity at t, then it is the same velocity. This 10.39 is also the velocity at c, and it's also the velocity at b. Alright, now let's solve for the solving now for the pressures pressure at C. Okay, so for the pressure at C, considering point O and point C. Okay, now let's apply the Bernoulli's equation. So point O, so I guess we'll just write the elevation head term because they're just zero. But at point C, we have P sub C divided by rho G plus, of course, the elevation at C, and what else? Plus the velocity head, VC squared all over 2G. Okay, now let's isolate this term, this P sub C. Therefore, P sub C is just simply the elevation ZO minus Z at point C, the elevation at point C. Okay, plus the no, that's not plus. That should be minus, right? Minus V sub C squared all over 2G, and then we multiply that to the unit weight. Okay, what is ZO? So ZO is, let's say this is our reference line. So point O as datum, as our datum. So this one would be 0. So that's negative, right? That's negative 1.5. So from point O to point C. So we have a negative sign already, but the point C with respect to this is positive. So that's the negative of the positive 1.5. A minus VC squared. Now what is VC? That's just 10.39. 10.39 squared all over 2 times 9.81. And our unit weight, since it's an oil, then that's going to be 0.8 times 9.81 kPa. 9.81. I think this one should be Newton per meter cube. Okay, so the value is 10.39 squared divided by 2 times 9.81, and that's negative, right? Times negative 1, and you add another negative, so minus 1.5, and we have this value negative 7 times these terms times 0.8 times 9.81. So we have a value of negative, let's say negative 55 kPa. Take note, this is our gauge pressure. Now you can also convert this in terms of the absolute pressure if you want. Okay, next is solving for pressure at let's say at B, considering point. We can use now point B and point C. Point B and point C. Okay, I think it's also fine if you want to use the point O and point B. I think that's just fine. But this one, this is also fine. This is also okay because since we have the same velocity, then the velocity head will just cancels out. Okay, now let's apply P sub B by divided by the unit weight plus the elevation at B plus the velocity head. Okay. Okay, so we are point B and point C, and let's say assuming or using point C as reference. Okay, so if these are a reference, then this will be 0, right? And our velocity head, since we are in the same, we are inside the tube, and the tube is constant diameter tube, then this one would be 0, this one too would be 0. And since we have an atmospheric pressure at O, then this also would be 0. Therefore, P sub C is just equal to Z sub B minus Z sub C, right, times the unit weight. So this is actually something like the hydrostatic equation. The unit weight times the changes in the elevation. Okay, so Z sub B is, right, so 1.5 plus 1.5. So from this is actually 0 if these are a reference point, and this one is 3. So 0 minus 3 meters, then times 0.8 times 9.81. Take note, this is 9.81 kilonewton per meter cube. So 3 times 0.8 times 9.81, that's I guess I think this term shouldn't be 0, right? So this is not 0. So we'll rewrite again our equations. Okay, so this is P sub B by rho plus Z sub B. This one is 0. Therefore, P sub C by rho G, okay, and these are 0. Okay, so our reference point is point C, so therefore this is our reference point. So anything going down would be negative. Okay, so P sub B, our pressure, since this is what we are solving, then P sub B is just equal to P sub C by this one minus Z sub B, okay, times the unit weight. Okay, our P sub C is negative 55. So that's negative 55 kPa. Okay, divided by the unit weight, which is 0.8 times 9.81 minus, okay, minus our Z sub B. Okay, so from this reference line going down, that would be negative. So minus negative 3. times 9.81 times 0.8. Okay, so that's 55 divided by 0.8 times 9.81. Okay, and then we have to multiply this to times -1, because that's negative. Okay, plus 3, and this is 4. Okay, times the 9.81 times 0.8. That's 31.4. That's negative 31.4 kPa. And this is gauge pressure. So this is our pressure at point B. This is our pressure at point C. And this is our velocity at point D. Now for point A. So for point A, we can just simply use the using point O and A. Okay, so point O plus the elevation plus the velocity head, 2G is equal to is the pressure head at A plus the elevation head at A plus the velocity head at A. This one, there is 0. This one is 0. And if our point A, let's say our point A is the reference point, then this will be our 0. So therefore, P sub A is just equal to Z, the elevation O at point O, okay, minus this velocity head term V sub A all over 2G, this is squared, okay, times the unit weight. Now what is the elevation at point O? So this is our reference line. So this is 1.5. That's positive. So 1.5 minus the velocity at A, which is 10.39. 10.39 squared all over 2 times 9.81, and this 9.81 is meters per second squared, whereas this one would be 0.8 times 9.81 kilonewton per meter cube. Therefore, 10.39 squared divided by 2 times 9.81. So what times 1.5 times 1.5 times 0.8 times 9.81. Oh, sorry, I guess this term, the velocity at A, right? The velocity at A is not the same as the velocity at B. Okay, so we are still in a large tank, and therefore the velocity here would also be equal to 0. So I'm sorry about that. Okay, this one should be also equal to 0, because this 10.39 is the velocity along or inside the siphon, but point A is outside the siphon, so therefore that's 0. So if you rewrite this, what we get is P sub A is just simply Z sub O times the unit weight. Okay, so it's just the hydrostatic equation. So Z sub O, that's 1.5 times the unit weight, 0.8 times 9.81. That's equal to 11.7. Okay, positive 11.7 gauge pressure. Okay, kPa gauge pressure. And therefore, for the summary, if this is our point O, our point A, B, C, and D, and if you wanna check the pressure, right? So if you want to check the pressure, our pressure here, let's say in terms of absolute pressure, so or just gauge pressure. So here we have a zero gauge pressure. At point D we have a zero gauge. At point A that's 11.7, and at point B that's negative 31.4. So that's a vacuum pressure, or a negative gauge pressure. Then our point C is negative 55. Okay, that's in kPa. In terms of the velocity, our velocity at O and A, that's 0, and here we have a 10.39. So 10.39, 10.39. Okay, so just a couple of notes before we move on to our next topic. Just be careful when you apply the Bernoulli's equation. Just make sure that the problem, that you can assume that the problem, that the frictions or the frictional effects of the viscous force can be neglected, or in other words, those frictional effects, they are way smaller as compared to the effects by pressure, by the elevations and things like that. All right. Now I'd like to introduce to you some concepts regarding the fluid flow and about the derivations of the mathematical expressions. And we said that when we apply the Newton's second law, which is expressed as F is equal to ma, and we take into account only the pressure forces. Okay, so still so I guess let me write it this way. Earlier, or in the previous lectures, then we had derived the equation that's called Euler equation of motion. Equation of motion for fluid flow along the streamline. Okay, and recall that we didn't consider actually the shear stresses, right? We only considered the normal forces, so that's just the pressure, but the shear stresses we didn't consider in the derivations of the equations. Okay, and we have learned that when we integrate, when we do the integration of the Euler equation, what we come up is the Bernoulli's, the so-called Bernoulli's equation. Okay, although the Bernoulli's equation, this was actually derived by Euler himself. Okay, so still, the concept is that we're still missing something. We're still not taking into account the shear stresses, the effect of the viscosity. Okay, and so if we write the timeline, this is Euler. So the timeline of Euler is 1707 to 1783, and before that we have the Newton's law, which is 1642 to 1727, right? And we have although the Bernoulli's equation, it can solve a lot of problems already. However, for some situations that requires the careful analysis of including the viscous effects, then we need another equation, and that other equation was actually provided by Navier, right? Navier and Stokes. So they are two different persons and different timelines. That's right, this is 1822 and then 1845, probably referring to the date when they presented the paper, 1945. So these two, they have a famous equation that's called the Navier-Stokes equation. Okay, so this equation basically an application of the Newton's second law, F is equal to ma, but considers, right, considers the frictional forces or shear stresses, frictional forces or the shear stresses. Okay, so this is more, the result of this is more, let's say, this is more complete as compared to the Euler's equation. However, the downside is that it is highly mathematical. So there's a lot of terms, highly mathematical, which are nonlinear partial differential equations. Okay, so it has included the frictional forces, except that it is highly mathematical. Therefore, it poses constraints on the investigators, because that's really a constraint if it is highly mathematical. And after a year or a century, I think that was 1904, this is Ludwig Prandtl has proposed a concept of boundary layer. So because of this concept, this this highly complex mathematical expression has been simplified. Okay, so it almost took like a year, right? And the concept of boundary layer is that, let's just draw right here. So for example, we have a flat plate, and then there's a fluid that's moving over the flat plate. Now, if we take the velocity profile before the flat plate, or before the existence of the solid boundary, then we have this, let's say, a uniform profile. However, as the fluid starts to move and it touches the solid surface, then it starts, the fluid that's adjacent to the surface would actually somehow like stick to the surface, so it will not move. And therefore, we will have something like a gradient, right? So it's like a gradient. So this one has the same velocity profile as this one, but near the solid boundary, it would have a non-uniform distribution. Okay, so at this point, so it's just the same. Well, the concept of boundary layer is that you will have a layer, something like this. It's just a very thin layer. It's just a very thin layer or let's just write this is our boundary layer. And in this region, or within this boundary layer, is where the viscous effects matters. And beyond or outside this boundary layer is viscous effects. Viscous effects are not significant, right? Or are negligible, we can write. Okay, so because of this, what it provides that it simplifies the mathematics of the Navier-Stokes equation. All right, so I guess that's just a brief overview. I'll just send links regarding the related readings about these boundary layer concepts, and it's really an interesting and a significant discovery by Ludwig Prandtl. All right, so thank you, class, and in the next video we'll start our new topics, which is conservation laws. So we apply the conservation of energy, the conservation of mass, and other things. All right. See you in the next video.